It's April 20th, 2024. We're about to go into Dead Week, and you are about to be harassed about context sensitive grammars. Context sensitive grammars, CSGs, are a grammar located between the context free and recursive grammar types in Chomsky's hierarchy. This means that not only is it more powerful than context free, but it's also weaker than everybody else's favorite topic of the course: Turing machines.
The context-sensitive grammar is defined by its distinct four-tuple, where n is the set of non-terminal symbols, sigma is the set of terminal signals, p is the set of production rules, and s exists within n, being the start symbol.
Formally, a CSG is a grammar where the left and right hand sides of the production rules are able to be surrounded by terminal and non-terminal symbols. In practice, it looks like this, where S goes to epsilon, or goes to another state that gives context for states after it. So let's see one in action. In this example, S equals a to the n, b to the n, c to the n, and generates the non-CFG. Same thing, with n greater than or equal to 1. So let's break this down into rules that we can understand. Our first two rules are going to be breaking down S into the first starting components, which are going to be A with B and C capitalized following it, or the second condition where we can go S into A and itself followed by BC. This will let us pull out all the A's at the start of the string for when we need to process them later. When we pull out all the A's at the start, you can see that the rest of our string is pretty jacked up. That means for our next couple of rules, we need a way to preserve the order of the original string. So let's make that happen. Rule 3 is just going to switch CB to BC.
Hey, wait a minute.
In theory, that sounds like a great idea, but in practice, not so much. You see, no matter what, we still need to maintain the form alpha A beta goes into alpha Y beta. Therefore, we still need to have all the context around these different pieces. So we have to break this up into 4 rules.
Wait a minute, why does this form even make a difference? Well, if we get rid of the context around these strings, then the grammar becomes an unrestricted grammar. Thus, it only becomes Turing recognizable, and it has a completely different power level.
So CB will go into CZ, CZ will go into WZ, WZ will go into WC, and WC will finally result in BC,
which effectively reverses all the B's and C's in the string.
Finally, we need to write down all the terminals for our program. So we've got almost all the A's, but now we got to deal with the capital B. So it'll be A capital B becomes A lowercase b, B capital B becomes B lowercase b, and so on and so forth for all the other combinations. Now, with n equals 3, let's see a real-world derivation of our string. Starting off, we can infer the following from the first 2 rules. Now that we've gathered all the A's at the front of the string, we need to sort out our B's and C's, so that way they're in order.
We'll do that using Rule 8 to deal with the specific A-B combo that we have starting out, and then we'll use Rules 3 through 6 in order to move all the B's in front of all the C's in the string. Now, in order to save some time, let's cue the time lapse. Now let's account for all the terminals using Rules 7 through 10. Finally, with all that said and done, you can look and see we have AAA, BBB, CCC because of Rule 10, and our string is finally accepted. Now, before we get to drawing the linear bounded automata, we need to actually understand how it's going to work. Well, take a look at this picture here. You may be thinking to yourself, wow, that looks like a regular old Turing machine.
What? It's just an ordinary Krabby. Oh my goodness!
Well, you'd be right, based off of how the transitions look and act the same as they do in a Turing machine. Surprised? Well, it turns out the major difference between a Turing machine and a linearly bounded automata is the tape, specifically its length. In a linearly bounded automata, you only have a set number of characters to work with. So now that we have a good background, let's talk about the closure properties of CSGs before we go to draw one and solve it for good. The closure properties are as follows: the union, intersection, and concatenation, followed by substitution, where f of s and a, being two context-sensitive languages combined, is equal to f of s and f of a, also context-sensitive languages. Inverse homomorphism, in which f of a is equal to s, where s is some string. And then the Clini plus operation, which functions just like Clini star, but rather than being where the number has to be greater than or equal to 0, there must be greater than or equal to 1 of those elements there. Now that we've finally gotten closure, it's time we solve one of these for ourselves. Now, given the language L1 is equal to w over a to the n, b to the n, c to the n, where a, b, and c all have the same length and n is greater than or equal to 1, give the grammar, perform the string derivation, and draw the linearly bounded automata. In approximately 5 seconds, I will reveal my answers for this, so feel free to pause the video. And without further ado, here are my results. Welcome back. Feel free to compare your answers with my results, and if you're feeling up for it, give this next problem a shot. And as always, good luck on your finals and have a good summer break. Bye-bye!